and today's our last day of boot camp, and we are very, very excited to have the expert on a cyber-physical system, or as he will call them, autonomous systems. So it's my pleasure to introduce Ufuk Topcu, who is a professor at University of Texas in Austin. So Ufuk is a very prolific researcher. If you would look his publication record, you will probably feel embarrassed and ashamed about your own. He's really publishing a lots of interesting and exciting work. His research was widely recognized by various awards. Let me just mention an NSF Career Award of IEEE Control System Society, Antonio Roberti Young Researcher Prize, which he just got last year. And thank you very much, Ufuk, for agreeing to give us this tutorial. And please, the floor is yours, or the Zoom is yours. Please go ahead.
Thank you. So this is recorded, right? I can take this first couple of minutes and show to my parents and make them cry with your introduction. That was an excellent introduction. Thank you. The bar is high, expert and all that stuff. Let's see what happens today. So this is, I was telling to Ruzika that this is hopefully a casual Friday. You guys have learned a lot, and I am not qualified to teach you on the formal what is this fundamental foundations of computer systems, because I am just not. So what I am going to try to do is tell you a little bit about what kind of research that excites me, and also hopefully show you some problems that with a little bit of progress and almost everything is wide open. I will have extremely sparse citations to people's names and work. And it doesn't mean that this is all what I know or I have done. It is just I have been lazy. Whoever is interested in following up on these things, I will be more than happy to give you as many pointers as you like. So I was tasked with cyber-physical systems, and coincidentally last Monday I had to teach my first lecture for my graduate's verification and synthesis for cyber-physical systems course. So I figured I would get something from those slides. And this is going to be a very brief introduction, hopefully. So this is I'm borrowing from Rajiv Allur's book. He defines cyber-physical systems as those that consist of a collection of computing devices interacting through communication with one another, exchanging information. And also, I guess the defining part is that the interaction with the physical world, with sensors, actuators, or whatever levers they have to interact with the physical world, and there's a feedback loop being closed. And if you go and look at what is happening in cyber-physical systems, you will find lots of books. And one of the common features is probably this convergence between control, communication, and computation. This is what is happening usually inside the system. And then I said, all these people are friends. I probably are missing some books, and I Googled cyber-physical systems and book. And then I came across this. So there is no end to this thing. Don't worry, it's going to end at some point. And these are just the books whose titles have actually cyber-physical systems in it. And there's an arrow. I did not see the end of this thing. It just rolls and rolls and rolls. So it is pretty established field, actually. There's quite a bit of similar flavor in all these books that they acknowledge this multiple facets of the problem or systems. And then there's also that typically and conventionally, these systems have been studied in the intersection of controls and formal methods and a little bit of a theoretical aspects of communication, perhaps. But it is growing relatively fast. So then some properties of cyber-physical systems, and this is where I will transition to, at the back of my mind, I will use things that relate to autonomous systems as a running theme. So obviously this interaction with the physical world and reactivity, it is an ongoing interaction. It is fitting the usual definition of reactive systems pretty nicely. And then the physical element is there. Typically, we build these things by merging heterogeneous components, and they try to integrate functionality. And that creates complexity. And then there are other sources of complexity or strictness of requirements that comes from that. They operate in an open world, and they have to make decisions as they go on. And the delays in communication and computation can become critical. And then you can take a system and put into a bigger context, like this picture I have at the bottom right, an autonomous vehicle within an infrastructure that also has automated elements to it, information flow, etc. Within the system and through the interactions of the system with the broader context, concurrency can come in many different ways. So these are just some of the properties that essentially make cyberphysical systems and autonomous systems very complicated. So one of the things is that many of these properties are what are happening inside the system. And I think really what makes these systems much more interesting is, and now we have been studying these kinds of properties for a long time, not that we have succeeded in everything, but we need new problems. Actually, looking into the broader context of what autonomous systems will do, in what kind of environments, for what purposes we will use them, just brings up an endless amount of new problems and complications. So obviously, they will be in dynamic environments. Things will move around them. We will not be able to predict what they will be doing. It is not just we put a system and just it works there within its confined environment without interacting with the rest of the world. And what they will do is not over and over again doing the same thing, or a simple going from a point to another point, but we want them typically be able to deliver complicated missions. I'm going to open a couple of things here. Just bear with me. And in order to be able to do all these things, again, there is the heterogeneity in decision making, and usually we deal with this thing by just building piece by piece and putting them together and hoping that when we put the decision-making elements together, they will be serving to what they're supposed to serve. And then nothing runs forever without glitches. They will be subject to faults, and we want to be able to deal with them as they go on. We cannot predict everything, every environment these will be working in. They will be deployed in unknown environments, hence their complications. They will not be in isolation from humans. There will be human users, and humans will want to use these things for different purposes in different ways. How they will be interacting with variations in the user characteristics is giving interesting problems, I believe, as well. They somehow need to understand their world. So they will, like we do, they will need to pursue what is happening around them and be able to react to those things. But perception is never perfect, or we cannot see everything that we want to see. That's going to bring in complications. And then as these things are deployed in interesting environments, they will use data, they will be observed by others in the world, and we don't want them to leak information about their operation or about their users in unwarranted ways. So that also brings in quite a bit of interesting problems. And we want to be able to do all these things. I usually put this in the center. The elephant in the room is really the verifiability. We want to play all these things and then be able to verify that these will not harm, pose risks to people, etc. Right? So verifiability is close to our heart, and I think it is at the center of what makes autonomy interesting and hard as well. So in various forms, so I'm going to touch on some of these aspects, but then let me go on a little bit more. So we have a hard problem, but we have been successful in various fields, right? It looks like AI is going to solve everything. When I was preparing this talk, I looked out there and tried to see what AI can do these days. And one of the very nice articles was that AI will be able to predict when we will die. That was the claim. I said, that's great. If AI can do it, I'm sure it's going to be able to drive my autonomous car as well. And then formal methods have been doing things properly for certain aspects of it, and control theory as well. So it may feel like everything is solved, but everybody brings in an element to it, and then also there are limitations, right? It may seem like you will be able to learn everything, and obviously the fanatics of learning seem to be claiming that, very prominent people. But then how are you going to verify that the system is going to be safe and satisfy all the properties that we care about? Formal methods will jump in, obviously, and say that I know how to verify software, surely I can do this, but then there are other complications that we don't have precise models adapt, things change over time, etc. And autonomous systems are not just software. Control may come in and say, look, within some maybe narrow context, I have been dealing with these things, and I have kept my airplanes safe. But on the other hand, what autonomous systems need to do is way broader than what controls have been dealing with. So long story short is that autonomous systems are nobody's comfort zone, and we need hybrid solutions. Okay, this is the idea behind this talk. And here's a little outline, and I will keep an explicit emphasis on that a couple of things will interact to solve interesting problems for us. And there are roughly 4 elements to it. First, for the first 2, I recorded some presentations and posted them on the Institute's website. So I'm not going to get too much into details. I will just try to give you the flavor. And the first one is this correct by construction synthesis of hierarchical control protocols. And it's going to be interactions between formal methods and controls. This is probably one of the areas out of the ones that I will be discussing that have been looked into for the longest. And when my students ask me, hey, why we are looking into these things, I need to have a fancy question to them to motivate them. So I usually use this question here. When we try to program in autonomous systems these days so that it does something, and usually it is in pretty naive environments, it is a very long trial and error. It is probably usually takes months to do that, maybe weeks. And the question is, if we face with a new mission, with a new vehicle, how can we do these things in 1 hour rather than weeks or months? If we can automate certain steps, maybe we can do it. Then the next piece is going to be the interaction between formal methods and learning, and for thoughts on verifiability and reinforcement learning. And that is going to be motivated by this question: how can an autonomous system learn how to execute a new mission in an a priori unknown environment? And I want to emphasize that efficiently and safely. No autonomous system will have billions of trials, and no autonomous system will be able to tolerate going and crashing tens of thousands of times on the streets and figure out from that. So we need to keep an eye on those properties. And the last question is how we cope with imperfections and limitations in runtime information. And I had not recorded anything on this, so I will spend a little bit more time on it, just planning in typically partially observable Markov decision processes. And I'm gonna touch on 2 different ways of approaching these things that we have been looking into. This is one connection is between formal methods and convex optimization, and the other one is going to be formal methods and learning. Okay, so I'm going to dive into the first one, and please interrupt me. I cannot speak for 2 hours. I can, but it is not enjoyable. So
maybe just like a couple of logistics. So maybe, Ufuk, would it be possible to, after an hour, to make a short 5-minute break that people can grab a coffee and if needed? Thank you. And everyone, if you post I will monitor the chat. If you have any question, just please post, and I will then tell Ufuk about your question. Thank you.
Okay, so let's dive into this first one. It's pretty dated, and so this is a little bit of a representative problem statement in quotes. Obviously, there's no actionable problem statement here. So given a system model and specifications in some language, so the system model is going to have both discrete elements and differential equations or difference equations or whatever to describe how the system evolves. It can be richer, typically captured as a hybrid system model. And obviously the system is going to have actuation limitations, and we will be subject to disturbances and uncertainties. And then another element is this specification element, which is extremely central. And we want to be able to encode what a user might want to do, our knowledge about the environment, perhaps even, and then the regulations or constraints that the system has to satisfy. And another element is that I have been emphasizing that it is an open world. We will be interacting with lots of other things around us. So we need to somehow restrict the environment in which the system is to operate. Otherwise, there's not going to be a controller that will achieve the requirements or the goals that we want to have if we think that the system might be subject to all sorts of craziness that is not realistic. And we want to be able to automatically synthesize a control protocol that manages the behavior of the system that we are interested in. It's going to react to the changes in the allowable external environment. And we want to be able to have an argument that the outcome is going to satisfy what we wanted to satisfy at the end. So I will definitely skip the next slide, which is the detour for specifying behavior with temporal logic. I'm not here to teach you temporal logic, but I want to say that some creativity has gone into in multiple fields, in robotics, autonomy, cyberphysical systems, whatever you call all of them, that temporal logic has been pretty expressive language for us to go and specify behaviors for these systems, all safe, allowable, required, or desired behavior of autonomous systems. So the details are not going to become relevant, so let's not get into the details, but in some form or other, there's going to be a relation to variants of temporal logic as the specification language in almost all pieces that we will be looking into. And going back, this is a hard problem because it has pretty rich dynamics and also relatively rich specifications. So the solution is never going to be a one-shot, hey, here's something, go and take it, and that's your solution, right? It's going to have multiple elements. So typically it is going to be a hierarchical structure. The names of these boxes are not important, but it's going to have multiple levels to it. And the connection is that each layer is going to deal with a different version of the model. And then it is going to try to address the relevant parts of the specifications. So it's going to decompose the problem in one way or other. And this is perfectly fine and nice, because in engineering, we already do things like this. We decompose problems into smaller pieces that we can deal with. And then let me just say a couple of things. As we go higher in the hierarchy here, obviously the models will become coarser. And as we go higher, the scope of specifications is getting broader. When we have continuous dynamics that capture the physics of the system, we probably only want to deal with the constraints on the continuous state and inputs. And as we go higher, we might want to look around us a little bit more. And as we go higher, even further, the example that I typically use here is if it's a driving example, the top layers might choose the highways or the streets that you want to follow. And the middle layer, now I know I'm going to drive on this street, whether there are cars around me, whether the lanes are blocked, whether the intersection is empty, etc. Stuff like that, so that you react to those changes. And once you decide that you have to go to the left lane, then the top bottom level layer is going to find a path that respects the limitations due to the physics of the problem, and find the path that's going to do that. And depending on what model and what specifications that you are dealing with. Obviously, the problem that you will need to solve is going to change its form. This is just some representative problems that might make sense. Typically, a finite horizon optimal control is at the bottom. If you have dynamic environments in your model for this middle layer, you may end up solving a two-player turn-based game on if you end up having a finite state model on a finite graph that I believe we got lectured on a couple of days ago, and then and so on and so forth. So the point here is, though, anybody can decompose any problem into as many pieces as you like. There's no limitation to that. You need to be able to do it in such a way that once you put all these parts together, you have a solution to the problem that you started from, right? And that usually relies on the consistency between the models that we use for each layer, all right? And the consistency means if this layer, for example, tells to go to the left lane, the bottom level should be able to find a way to go to the left lane, all right? And that means when we create the abstraction for the middle level here, we should not include the possible discrete directives that may not be able to, the bottom layer cannot be able to implement. And that's the consistency between the layers, and obviously that consistency is kept track through simulation relations. And how you can come up with abstractions for each layer so that you maintain that consistency is what has gone into quite a bit of research in this field. And there are some ideas that for each layer, you might have to bring in and ask yourself how I can maintain a simulation relation between these different layers, depending on what model representations you use in each layer and what specifications that obviously you want to be able to keep consistent across the layers. I'm going to now dive into, let's zoom into a little bit of a piece of part of these bottom two levels, just to give you a little bit of an idea what might go into that. So bottom level is, let's say we deal with a difference equation, discrete time but continuous state model. And this is the workspace that we have, X is the workspace. And then it usually goes along the lines of you discretize the space into finitely many cells and associate a discrete state for each of those cells, the labels of those cells. And the next thing that you want to do is decide whether I should include this transition from a discrete state to another discrete state. And in order to be able to keep consistency, one way is you go and ask questions like, no matter where I start in this cell, whether there is an admissible control signal that's going to take me to this cell, somewhere in this cell. And so more precisely, a little bit more precisely stated here, whether there exists a control signal and some finite time such that for all times between the initial time and the final time, I stay inside the union of these two cells. And at the end of the time interval, I am in where I am trying to go, i.e. this cell, somewhere in that. I just want to be in that. And I want to be able to do it in such a way that this holds for all initial states. So the quantifier on this starting point is for all, and quantifier for the final target set is there exists. And I want, if there are disturbances on the dynamics, we want to be able to robustify against all possible disturbances. And if somehow this brutal test is passed, we go ahead and include this transition. Okay, because I know if I ever come to the cell that corresponds to this new 5 here, there is a way for me to go to the cell that corresponds to new 10. And then you fill in that by asking all these pairwise questions. Then, based on this abstraction that you have here, you might solve a reactive synthesis problem that we looked into. And let's say now the outcome of the reactive synthesis problem is this discrete sequence. That the meaning of that is, if you follow that discrete sequence, we will satisfy the specifications that we had. Then, because of the way that we constructed these transitions between the discrete states, we will know that there exists a continuous trajectory that's going to ensure that we follow this high-level discrete sequence of states. And then that's going to give you the fact that even the continuous implementation, if you monitor it in a proper manner, is going to satisfy the specifications. And this is usually referred to as correct by construction, and the construction part is this construction of the abstractions that you use for each layer. And the correct is that now I am correct with respect to the specifications. And the procedure is brutally and in a brute force manner constructed, that you ask zillions of questions of this form for pairs of cells here and try to answer them. So good and bad news here. If we could do it, now we have finite state representations. A lot of things that we know from formal methods, we can go and use them. Good, but the bad news is that probably there are 2-3 different disciplines that try to solve problems like this by itself. So that it is not an easy problem necessarily. But then, after all, there are no easy solutions for hard problems. We just change the nature and look of the difficulties. And then, over time, people have realized that some of these problems can be solved in maybe a little more efficiently and systematically than others. If the dynamics are linear, we have some hope. And for certain types of nonlinear dynamics, maybe through approximations, we can solve it. So there's a connection from here to approximate simulation relations, etc. So let me show you just a little bit of you take a sip of your coffee, and if you're in Europe, maybe wine. So here's the little example. So this is a quadrotor that we will be controlling. And these two will be quadrotors that we don't control. They are controlled by someone. They don't fly themselves, but the controlled quadrotor does not know how they will be behaving. And the specification for this controlled quadrotor is going to be visiting this point. I'm making it up. I don't know exact points. This point and this point repeatedly, something like that. So that could be post office, I don't know, bakery and whatever that it wants to go every day. And these are the bad guys. We don't know how they will be behaving, but we have this prior knowledge that as part of the environment, this quadrotor is, after all, a physical object. If at one moment I see it here, at the next moment it is not going to jump up and like appear here. It is going to be along this line, this moves. Along this line, it moves. These are the police patrols. They just do that, okay? And they respect some sort of physical constraints on their behavior. So, and then we applied this hierarchical structure that I mentioned. At each time step, now I cannot keep track of the controlled one, but it is on the one on the left. Essentially, it sees the world, and then tries to make a decision where to go. And it is not that it always avoids the patrolling bad guys, let's say, but it tries to strategize, hey, I need to wait now, and then, okay, all of them are on that side now, I can probably go through, etc. And it does what it was promised. You can obviously see that there's some turn taking in this implementation. It sees what is happening and then takes its turn. And nobody promised that there's not going to be a turn taking, because after all, we try to come up with this behavior by solving a two-player turn-based game, right? And even from here, we can now come up with zillions of further complications of all this business. That's how to not do it in such an explicit turn-taking manner. And we can discuss them separately. I'm not going to get into these things. Okay, so this is the end of it. This is the first part. Controls and formal methods have interacted to solve a synthesis problem. Neither of them was accustomed to solve or even able to solve because one side did not want to play with continuous state dynamics and the other side was oblivious to rich behavior specifications. And when they work together, they have been able to do something. So may I offer any clarification at this point, just so that I can drink some water? No questions? Raina, you promised me questions earlier. Just let me just remind you. Hopefully you will ask and help me a little bit. Okay, so I'm going to go now to the next piece, the verifiable reinforcement learning. Why am I even discussing this? There are, I think, a good number of reasons that we cannot close our eyes to learning. And I'm going to try to show one good reason and then a couple of bad reasons later. Not bad reasons, but I'm skeptical. So everything that this field I described did over one or a little bit longer, 1 decade or longer, I'm going to put now in this very nice synthesis box. And let's look at what has been done there. What has been done is some environment description, some requirements, some maybe even performance criterion is given, and we come up with this F. And F in this case may refer to this hierarchical structure. It's not just some function F. So a very, very central assumption is that we already know the environment description, the specifications are nice, everything is nice, just very precisely given, which is good. I am not against precision, but in reality, we will lack such sharp descriptions of what we need to do. So one of the things is that we may not know exactly what the environment looks like, but we may interact with the environment offline or online. So that's a reason maybe learning could help us. Then we give very nice descriptions of temporal logic specifications and performance criteria, etc. And in my experience, only CS professors and some group of grad students can speak temporal logic as their second language. And usually the normal users cannot do it. But we want people to be able to use it. So there is that mismatch between what our tools can take and what normal users can express, which is fine. This is not a criticism to anything formal. This is just a pointing to a gap, okay? And then we live in a world where even if we actually go and isolate ourselves from the rest of the world, maybe somebody's going to come and knock on our door and say, AI has done this. AI is going to know when you will die, for example. So we cannot stay away from learning. If you are developing an autonomous system, even if you say, no, I'm not going to use any learning-based anything, somebody's going to come bring a module, something into it, or you will need to interact with it, right? So you might get information from outside that relies on some sort of learning. So we can make this list longer, but after long debate with myself that I was convinced that we should look into problems that are in the intersection of learning and synthesis. And in the recorded, pre-recorded videos, I gave a little bit more historical view on how these things had evolved in my mind. The initial point was I did not know what learning was. One of my postdocs brought me a paper by Leslie Violent, and he talks about probably approximately correct learning. And I thought, okay, this looks pretty precise. Maybe we can take what is in there and then try to insert some formal methodsy thoughts into this. For example, temporal logic constraints, how we can learn behavior that is constrained by temporal logic, etc. And I'm not going to get into those. I'm just going to give you a couple of glimpses of different things that we have done, for example, for safety and efficiency purposes. And reinforcement learning serves as reinforcement learning serves as a problem description that we can take and look into how we can maybe do things slightly differently. And here's a 1-minute crash course on reinforcement learning. There is an agent. It does not know certain things about an environment or about what it needs to do. It takes some actions. They are implemented in the environment. Things change. The agent gets to observe, and maybe somebody comes and starts giving thumbs up or thumbs down on, hey, do it this way or not this way. And it can make pancakes. It can play board games. It can fly quadrotors. Everything is nice, but also it can create behavior like this. This is I believe, a reinforcement learning trained agent that bot. And even though it might be fun to be on that, we probably don't want to do things as this bot does. Then we said, let's put a new piece of problem data as a temporal logic specification. And a specification in this context is going to play a couple of roles that I'm going to mention. But as its usual reference, we can ask whether a learned strategy is going to satisfy the specifications. Or a more interesting problem is whether during learning, we can ensure that we never violate the specifications, or at least some safety fragments of the specifications. And another way of specifications may come into learning, I believe, is that they are very nice representations of knowledge that we can feed into algorithm development. Hence, if we have prior knowledge that we don't necessarily relearn over and over and over again, we may be able to encapsulate knowledge in the form of temporal logic specifications and see how it actually can be integrated into learning to make it more efficient. And then there is the flip side of the coin, this notion of inverse reinforcement learning.
Ufuk, there is a question about synthesis and learning from Maria Paula. Maria Paula, shall I just read it, or do you want to state it loud? Okay, let me then just read it. What is the reward structure in conventional synthesis and in synthesis plus learning respectively?
What is the reward structure? I'm not sure if I can give a precise answer to that. But in conventional synthesis, in reactive synthesis that I touched on, and probably the parts of the week that we have looked into two-player games, I don't think that we had a reward structure per se, right? It was only the winning conditions were whether you satisfy a temporal logic specification or not. But after all, these things generate behavior over some state space, and they visit certain places. So you can easily put a reward structure as a function of the states, and actions, or whatever you want, whatever the right thing is, and form these games that we looked into this week with some objective on, hey, do these things in such a way that you satisfy the specifications while maximizing, minimizing some reward, etc. And it is the same thing, I think, in reinforcement learning over finite state spaces. It is just a function over the whatever you care. It could be states, it could be, I don't know, even sequences of states, maybe, over what you see, the observations or actions might cost you something. Essentially, it is a map from, let's say, for simplicity, from the states to some reals. Does it answer the question? Because it was asking about the structure, and I don't know if I answered the structure.
Yes, thank you. Well, the question was related to slide number 13, because since there was the line known fixed temporal logic constraints plus reward structure under conventional synthesis, the point about known fixed temporal logic constraints was very clear. But then there was this line about having a reward structure in conventional synthesis, and I didn't know what you meant there, and I was kind of expecting, just like there was a comparison between the two kinds of synthesis, about the temporal logic part. I was expecting a comparison also for the reward structure, and that didn't come. So I had like a question there, but now it is better. Thank you.
Okay, so I did not think about that deeply. I just throw it in because some part of the world loves rewards. Conventional reactive synthesis, I don't know what conventional reactive synthesis means, but reactive synthesis by itself does not necessarily have a reward or reward structure. But I think we can naturally define, put a reward structure. You can put anything on anything that you like. Whether it is going to be a problem that you can solve is a different question. Let me just say that much. Reactive synthesis doesn't necessarily perhaps have rewards, but there are versions of those problems that we can introduce rewards and try to tackle.
To also say that, Maria Paula, we will have in the synthesis workshop, we will have a tutorial on reactive synthesis where I guess maybe the speaker will go more into details about rewards and things. So Ben will be the speaker on reactive synthesis. But maybe, Maria Paula, does this answer your question, or do you have more?
Yes, thank you. And also thank you for the further pointers to other material. Thank you, Ružika. Thank you.
Thank you. And Ufuk, one more question from Anna. Anna, do you want to unmute yourself, or shall I read it?
Yeah, I can, yeah. I had actually, please, yeah. So I second Maria Paula's question. I also had a question about that, but I guess it's now resolved. It's just, for me, this conventional synthesis doesn't really guarantee performance, and that's why I was also questioning this. But I had a different question. The different question would be, so we have, let's say, a specification that we want to satisfy during learning when we are learning something. Like you started talking about this. And does it guarantee that when we deploy the learned system, the specification will be satisfied?
Excellent question. You can ask that question, right? I don't know how to answer it. What I can tell you that hard to discuss because there are so many moving pieces. But at least if you're deploying in the environment in which you trained, you want to be able to satisfy the specification, right? If at least you don't satisfy that, you probably haven't done enough. It would be nice to be able to deploy in, you know what I'm going to say, but I cannot say it because I don't know how to even discuss it, but somewhat different environments. And a couple of levels. Hope that things will not break utterly. What would be even nicer is that you somehow predict, if you can give a characterization of what kind of variations in the environment might be viable. You want to be able to predict how bad things will go. I believe after training, prediction part is if you can give a characterization of the new environments, that we can probably give answers to that. Learning in such a way that you will naturally be nice in new environments. I don't know. Just actually, probably after this call, I'm going to go and discuss 3 relevant problems with my students. I think this is wide open. I was actually surprised. I'll come to that later, but let me just comment on that now. We did a little bit of work on inverse reinforcement learning, where we incorporated temporal logic specifications as side information that says that everything in this world is going to happen in the way that this temporal logic specification describes. And I was very naively hoping that would give us a little bit of non-brittleness for environment changes, but I was utterly wrong. So here's a little, very tiny example. You have 2 rooms, and there's a wall in between them, and there's a door. And you see demonstrations that things go through the door, and from that, and you incorporate that, you go through the door. You learn something, and if you go and deploy the system in the environment in which that you trained, everything works beautifully. You satisfy your specifications, things are nice, etc. Even the tiniest change where the door is, like move the door a little bit along the wall. You know there is a wall there, wall hasn't changed. The door tiny bit moved. Things break pretty badly. So I was hoping that this high-level knowledge that we incorporate would actually help in that. But what is not happening is the following. The knowledge that we incorporate is unfortunately about it refers to the location of the door rather than that there is a door. So I think I'm just jumping ahead. Let's go on, but we can discuss. And changing environments is weird, okay? I'll comment on that back again. There are some things that specifications help with and some things that not yet. Okay, so the first element is safety via shielding. Okay, this is obviously going back to the work that Roderick Blom's group had initiated, and they also are part of this. So this is the conventional reinforcement learning cycle, and what we will do is we will introduce this runtime shield here. It's going to have access to the actions, and it may see what the learner sees, and it's going to be able to modify the actions of this learner. So a couple of like properties here. We want it to be corrective, the shield to be corrective with respect to the safety part of the specifications, so no safety violation. And that since the shield can modify the actions, you can actually pretty trivially do this thing if you don't allow the learner implement anything. If you can change everything the learner tries to do, then you can do. Obviously, that's not useful. We want the shield to be minimally interfering, and the shield is going to be synthesized from a high-level coarse abstraction of the environment, and that is sufficient to interpret the safety part of the specifications. And only that, it is not going to refer to the inner workings of the learners. Hence, it is going to be actually agnostic to what the learner, how the learner was built. So it can work with goofy learning algorithms, including that use neural networks as their function approximation representation, and possibly even over continuous state spaces. So the learner might be acting over a continuous state space, but the shield has a neat, coarse, high-level, discrete view of the world. And if the learner has some desirable properties like convergence, we want the shield to not mess up with that. And it is not going to be able to converge what the unshielded nominal learner converges to, because that behavior may not even be acceptable with respect to safety specifications. But we want it to be converging to at least constrained optimal solutions. So to some extent, we were able, there are ways to prove these properties that if you build the shield in an appropriate manner. And then there are these empirical observations that we made that it may actually help with the learning performance as well. This is totally empirical and case by case. And the shield synthesis itself it takes a coarse representation of the world, and it takes a safety specification, and it comes up with a monitor. It just solves a couple of different games essentially over finite graphs. All right. And hopefully that reactive synthesis workshop could give more details on how these shields can be computed. Nevertheless, though, you first come up with a couple of elements that monitor whether you violated, how much you might be violating, what the reasons for violation are, and then it uses that information and it comes up with a permissive strategy to satisfy the safety specifications. And out of all possible ways of correcting with respect to safety specifications, you choose one that actually corrects in the fastest way and delegates back to the learner as quickly as possible, and that relies on a book again. And so this is a little bit story behind this. When we tried to do these things, we said, let's pick a trivial example first, okay? So that we can check whether this stuff is going to work. And I thought a car trying to drive around a circuit like this would be a trivial example, because if you go to YouTube, you will find zillions of examples of presumably things are being learned in this way and the cars go around circuits. And then we started implementing these things. When I say we, I usually mean a poor student, started to implement these things. And the plain reinforcement learning part of it did not work. And then he started coming, hey, I need to optimize this, parameter optimization or hyperparameter optimization. So there's a thing called hyperparameter optimization, by the way. If anybody wants, we can discuss that later over sufficient amount of wine. So it did not work, and then a bunch of hyperparameter optimization. We got the reinforcement learning without shielding working, and essentially the left side is non-shielded, and the right side is shielded. It is just all over the place here. It tries a couple of things, it crashes, and it comes and restarts as the reinforcement learning algorithms do. It has pretty hard time in creating any legible behavior here, and it crashes zillions of times. The version with shielding actually figures out a way to complete this task in much shorter training and with no crashes. And the no crashes is actually it is only not a property that we like, but also it enables that you learn a little bit, quite a bit faster. The reason is that if you don't crash, you don't have to go and reset this thing. So it does certain things in randomly, but it continues to at least inch by inch make progress toward, by chance, seeing a full circuit. And if it sees it, it gets a reward, and it understands that, okay, this is nice, I should be doing this. So no crash essentially increases the likelihood of actually getting some reward from whoever rewards you. This one is crashes, resets, crashes, resets, crashes, resets. It is delayed for it to see any reward. So it takes much longer to figure out, what am I doing in this world, okay? And then there are some other cases that small Pac-Man environments, the shielded version nails it. It plays better than I can. Not a high bar anyway. And then other people have been able to work do these things over much larger Pac-Man environments with ghosts, multiple ghosts, and etc. And the reason is, again, the one on the right is never eaten, hence it figures out how to play this thing much faster. Okay, so that is that. The next question, so this is the safety part, just one example on how formal methods can help us try to keep some safety. Yeah.
Ufuk, Raina posted her promise question. Raina, do you want to unmute, or shall I read it?
Yeah, I can unmute because I wrote it just shortly. So what I wanted to ask is about to synthesize the shield, you need some abstract model of the environment, right? And then in different situations that needs to be more or less precise depending on kind of what your environment is, right? And what is the problem. So it's not kind of.
Yeah. I cannot tell you what exactly the model here is in this example. I just don't know.
Because here I can imagine that one can kind of abstract a model of the environment, and then that is sufficient to guarantee that that the car doesn't crash. But if it's a real car, right, it's it shifts the problem to how do you guarantee safety of a real car in a real kind of urban traffic, right? And then it's not.
Just totally. We have been pushing it under the rug, and again, a hard problem is not going to become easy.
No, not that, yeah.
But what I can tell you is that, like, if it's a if there is an MDP, large, maybe even continuous state MDP, the way that I have been thinking about this and keeping myself a little bit happy about these kinds of results is that knowing precisely what state you are at is very likely not necessary for you to reason whether you will be able to stay safe or not. So you can abstract out the precision of the state representation. And you may also actually work, instead of working with precise understanding of the transition probabilities, you may be fine with some existence of transitions and the structure of the MDP, but rather than the transition probabilities. And if in this case, if the safety is implemented as merely crashing on the wall, a representation could as well be whether you are close to the wall and whether you are going toward the wall, right? It could be as simple as that. It depends on what safety specification, at what level that has been specified, and how can you have a dynamic model that is going to help you reason about the behavior with respect to that specification.
I guess it boils down to identifying problems that are properly decomposable in that way, that for safety, you really need a lot less information than from the environment than for guaranteeing the performance, and essentially decoupling the two and kind of getting the best of both worlds.
Getting something from the both worlds. Hard to claim that you get the best out of both worlds, but you look at the both worlds. Yeah. Okay, so the next question is, if there are similarities between the two tasks, that's okay, let me step back. You have two tasks, okay? And in the sense that there is an environment, and there are these regions of interest, and in both environments, their shape, location, etc. are different. This person who actually looked into this problem likes timed logic more than non-timed, so there are clocks. And with respect to these clocks, you go and write some specifications. No, you don't write specifications, sorry. So let me step back. We have these two environments. There is some underlying task that might have some time-related elements as well. So we want to learn how to execute this thing. And so the premise here is that if you brutally take the pain in one environment for learning, whether we can leverage that effort and what we had figured out to expedite learning in a different but related environment for a different related task. Okay, so do your usual learning here, however hard it is, then see if you can expedite this side. And the flow is the following. So for both, you collect some data. And then you try to infer what formulas might explain what you are seeing in this world. And then there is a relatively precise notion of a logical similarity between these two. If you declare that these two formulas are similar to each other, then whether we can do something with that. All right, so this one goes all the way to learning, and you learn whatever you learn. And now we will ask whether we can expedite this reinforcement learning part of it. Based on that, we discovered there is a logical similarity between the two tasks. So I'm going to copy these two pictures in the next page, and I'm going to show you 4 results here. One is that the learning method is the so-called Q learning. It essentially goes and figures out and keeps track of what the rewards are, etc. And based on that, tries to come up with a policy. So the black one shows the optimal behavior is collecting 100 rewards. The black one shows this plain learning, and it just tries to do a couple of things, and it then starts going up, but then it levels out, and we run this thing for 50,000 steps, but you can run it for 2 million steps, 5 million steps, whatever. This continues to improve slowly, but never even gets close to the optimal behavior levels. Then what we do in this target environment is, first of all, start now incorporating the specification that we had found. Essentially, now learning is over some appropriate product space. And then there are multiple ways of inferring these specifications with different cost functions. So this pink one shows the learning behavior with this temporal logic specification incorporated, metric interval temporal logic specification incorporated, and this specification had been inferred using one of the criteria for judging that the specification that you learned is a useful one. And we get this pink one. So it is already pretty much better than the black one. And if you use a formula that is inferred by using a different criterion, we get this blue one. And then if you warm start by using the underlying policy from the source task, source environments, the underlying policies, then we obtain the red one. So what we see here is that, yeah, we can expedite the learning in the target environment if we just try to do what I described. And a couple of things, these red one, pink one, and blue one, if we could look at it carefully, they don't, there is no movements here for the first 10,000 steps. That's the data that they use to figure out whether there is a logical similarity or not. There is no reinforcement learning happening in that window. The black one has these wiggles here because it starts to see things sooner. And then after waiting for that amount of samples, the red, pink, and blue one actually go up pretty quickly. So this is a step toward, if there is knowledge that we can try to discover, or we have a priori that you can incorporate it in that reinforcement learning and make things more efficient. And the other side of which, before I take a break, the other side is this inverse reinforcement learning, and I have to say a few words so that you can, what we discussed with Anna is going to make a little bit of sense. So the inverse reinforcement learning is a little bit different. It is used for several purposes. So let's say we have an environment. Somebody took our robot or whatever, and it started showing us these, what's called demonstrations. The person drives the system in this way. And it takes another, it does another demonstration. I don't know what, similar but different, okay? So we have certain number of demonstrations in that. And now with this demonstrations given, the underlying model of the system given, we try to come up with a reward function that's going to, when we optimize with respect to that reward function, is going to generate a policy that mimics the demonstrations. You come up with a reward function that gives you a policy, take that policy, run in the system. You will see behavior that is similar in some sense to these demonstrations that we have started from. So that's inverse reinforcement learning. And specifications in this case come into play as side information. And side information is the following. So let me just give you this example first. If this is a driving example, the demonstrations may be how a particular driver drives, whereas the side information may be the traffic rules. In a sane world, every driver follows the traffic rules. So we don't have to learn them from scratch. In this little example, in addition to these demonstrations, these say you always start from this blue thing, you avoid these red things, and you go to the green things in this order, first this one, and then eventually just you end up being in the yellow region. I believe these specifications say that. And then we want to generate a reward function that not only mimics the demonstrations, but also tries to improve or somewhat maximize the probability of satisfying these specifications that we started from. So that's the problem statement. And let me skip how we solve this, but essentially the solution, just one solution to this, is it builds on the so-called maximum likelihood inverse reinforcement learning, some parameterization of the rewards, and then from that a specific way to go to a policy. And then the cost function is trying to make to choose the theta corresponding to the policy pi sub theta in such a way that the behavior is similar to the demonstrations when the policy is implemented on your Markov decision process. And then instead of running the inverse reinforcement learning over the MDP, we run it over the product space, over the product MDP, and we keep track of the possibility of violating the specifications and penalize the violation probability in this thing, so that the methods behind maximum entropy inverse reinforcement learning can be used to solve this problem, or try to solve this problem. Here's an example without side information and with side information. It is the same map that I have been showing, and blue means low probability of satisfying the specifications and yellow means probability 1. If we don't incorporate side information, and the colors are, if I start from the shown cell, what is my likelihood of satisfying the specifications? And there are lots of blue regions. On the other hand, every cell has almost red colored, almost sure satisfaction of the specifications, regardless of where you start from, unless you start from these red places already, because you would have violated the safety, the specification already if you started from those. And why do we have it? I think the explanation is pretty easy. If you look at this picture, in these regions, we don't have any demonstrations. There's no data whatsoever. And if we go to this picture, these areas where we don't have data is bluer than where we have data. So specifications help us actually generalize with respect to the satisfaction of the specifications over the places where we had not seen any data. And is this at the expense of being not similar to the demonstrations that were given to us? These figures essentially try to explain that, at least in this example. We satisfy the specifications and the behavior that we generate is still quite similar to the demonstrations. If you have seen demonstrations in these areas, and if you start in these areas, you will be like them, but you will still satisfy the specifications if you start at other places. But this is not changing the environment. If you change the environment even a tiny bit, if take this one and put it here, things break. So maybe ideas of the previous type, hey, the environment changed now. Can I figure these things out with less computation, less data? But yeah, those are not fun games. That I don't see that much of interesting research in that. Somebody needs to do it. Okay, let's take a break.
Okay, let's continue at 49, whatever is your time zone. Is that okay?
Yeah.
Okay, then let's continue in 5 minutes.
Tu cherches quoi? Le chargeur. J'en ai un là. Un vrai, oui.
Merci. Merci.
Okay, it looks that everyone is back. Ufuk, are you ready for another round, or you had enough of us and our questions?
No, I have not have enough questions. Please have more questions, and I'm ready.
Okay, so someone has more, please. Whoever has more, please shoot. Anna, that's you, please.
Yeah, I have more. So I was wondering, in this logic learning, when you learn logical similarities. So this is really nice approach because it guides this exploration, and it's really cool. How important is the MI in MITL there? So is this what's guiding the exploration?
So the MI part is, it is cheating logic, right? You have these numbers so that you can write mixed integer linear programming problems that you can study optimization throughout just the appropriate optimization methods that you can use it, right? And that is what the person who actually worked on this was familiar with. Later on, we tried to look into what Daniel Nider from MPI in Kaiserslautern and a couple of others, not necessarily doing it MILP, it's just, sorry, what is it? Metric interval temporal logic, but more discrete, just sheer discrete logic. And it seems to help in a similar manner. There has been work on both if you know something, how to incorporate it so that you make the learning faster. There's no target or anything. But then also there are quite a bit of extension on not necessarily doing it early on and then using that first infer and then learn. So Daniel obviously had been working on automata learning. So there's a joint automata learning and reinforcement learning. They run in parallel, and you have a loop. You obviously every time you get something new through automata learning, your automaton changes. They incorporate it into reinforcement learning, and similar or actually better improvements are possible. So that is not dedicated to that. I think this idea of using some sort of logic to encapsulate knowledge, which is algorithmically actionable, and incorporating that into learning it has very different flavors. That is pretty universal. Then the question is, can I develop algorithms on that? Whether my learning algorithm will be able to take advantage of, whether I can actually run the learning algorithm with that knowledge incorporated now. There are lots of different levels of questions that we can ask. And I think it is wide open still. And I am very much pissed at myself that when the environment changes even a tiny bit, things do not work. I think that might give a nice discussion for the rest of the semester. I feel like we are not taking advantage of knowledge sufficiently.
Yeah, so I would be happy to also discuss this.
Yeah, sure. Okay, I will be happy. So the last piece, POMD piece. And why POMD piece? Because why not? It is just, everything is a partially observable, but we just pretend that it is not. Now let's put it in. So the approaches that I'm going to show here are how can we cheat but get somewhat useful solutions? Because it is just hard, right? Synthesis in POMDPs in every form is hard. There is no, I think we touched on this yesterday, we must have. So restriction to finite memory strategies. So in general, you might need infinite memory. Restriction to finite memory strategies may give you a working environment, yet still hard, and it's going to induce suboptimality. So randomization might come in as randomized policies might give you a little bit more. without having to use extensive memory. So these are the type of thoughts that had been going into what I'm going to discuss today. Question? No. Okay. Good. So, all right, good. So let's move on. I thought there was a question, but there was not. So this is the type of thoughts that will go, and then I'll first try to make a connection between formal methods and some sort of convex optimization. And then I said POM-DPs, but I will not talk about POM-DPs. I'm going to talk about a related problem. I'm going to talk about synthesis in parametric parametric MDPs, parametric MDPs, and Markov chains. Okay, and the reason comes from I don't know if others had made it, but to my I guess knowledge, it comes through the work by people around Ufuk, Cartoon, and Bernd Becker, and the realization is that if you take all finite state controllers implemented on MDP with some bounded fixed memory can be represented as a parametric Markov chain. So, and then I'm going to get into parametric Markov decision processes in the next slide. Markov chain is, yes, it is what it implies, that you take a policy and you induce a parametric Markov chain. And then there is a correspondence between a strategy, finite state strategy for a POM-DP, and the parameter instantiations in this parametric Markov chain. So we'll try to leverage this correspondence. So for now, let me now go to parametric MDPs. So it is a MDP, Markov decision process, but the transition probabilities are not specified, and they are parameters. In this case, P1, and obviously this one is going to 1 minus P1. This probability here is P1 square. This picture is probably missing something, because if P1 is not 1, something is missing there. Anyway, so the long story short is, instead of having numbers, specified numbers, we have parameters that had not been specified. And then we will try to throw in some specifications. Maybe the probability of reaching a target set is less than something, or ever going to some undesired place, the probability is smaller than something, and some performance specification in the expected cost form. These are not necessarily what they mean. Let me put these in quotes. So this is some sort of performance specification, and this is some safety specification. Then the question that we will look into is, there's an objective function, whatever that is, some f from the parameters to reals. So the question is, given a parametric Markov decision process M, find an instantiation of the parameters, these guys, along with a scheduler or a strategy over this MDP, such that once you put the parameter values, that these things, and then the scheduler, you end up having a Markov chain. You want to satisfy the specifications, and while you are doing it, why not optimize some other objective function over the parameters that you want? And the objective functions maybe, I don't know, if this could be modeling a model repair problem. I have my probabilities, but I want to change the probabilities in some way, so I might have introduced some parameters. So repair it in such a way that the change from the nominal values is small. That might be a metric, but you can come up with all sorts of other things. So this is just a problem statement. And here's a solution. So this is a solution, essentially nothing much different. You just follow what you would do for perhaps for solving a policy synthesis problem for a Markov decision process, but obviously we have many more pieces to it. So we will, in addition to the parameters in the problem, which will appear in this transition probability matrix here, the parameters are there. We have these extra variables to keep track of the random scheduler that we will be looking for. And the PS will be the probability of reaching this T from the set T from state S. And then the expected cost of reaching G, this other thing that we used in the performance criterion, is going to be kept track of as C sub S. Essentially, there are like the parts of the problem is this is the objective function. These are bounds on the probability from the initial state. So from where I start, I respect the constraints that I have. And then the rest is that you have a well-defined scheduler and parameter instantiation. And then you keep track of the, recursively, you keep track of the, whether the safety specifications are going, what the probability of satisfying safety specifications will be, and what the expected cost is going to be, again, recursively from where you are. So this is not surprising because we had seen lots of optimization problems in similar form. What is going on here is probably, I'm going to focus on this one bit here. So, and I copied in the next page. So what is going on? There's nothing goofy here. But what happens is this includes decision variables. This includes decision variables. And this has the parameters in it. And the parameters themselves may actually be even nonlinear functions of the parameter. The entries of this P may be nonlinear functions of the parameters. So because of these kinds of complications, the problem had been regarded as just a nonlinear programming problem, and then you would solve it as a nonlinear programming problem. But there is quite a bit of structure in this form. So what happens is that actually it is in the form of if these are polynomially dependent or affine dependence, this entire thing is going to be in this form. Okay, that entire thing. So there's going to be a coefficient, and the variables raised to certain powers, then you multiply them. So some monomials in terms of the variables that we have, and some coefficients. It is that structure. It is nonlinear, but it has that structure. And then a little bit of a terminology. If this coefficient is strictly positive, this kind of function is called polynomial. And then if there's no restriction on the coefficient, it is going to be called a signomial. So the question is whether we can exploit this structure or not. All right. And it turns out that not necessarily directly, but through some approximation, you may be able to. So this is the problem that we start from. And then we restrict our attention to parametric MDPs with signomials everywhere. The nonlinearities are signomials. Let's go back. So we will work with signomials in this form. All these nonlinearities will appear in this form. And then that problem itself is not necessarily anything nice. That still leads to this nonlinear program. But then there's a very much related problem, which is a geometric programming problem. And it restricts the attention to polynomials in the cost function and in the inequality constraint. And the equality constraints, these can only be monomials. So there's no summation, just mono. If I go back again, the equality constraints can only have one of these things. It cannot have a bunch of multiplication and then summation. It cannot have that. So if the problem was in this form, which is not because we have signomials instead of polynomials, geometric programming problems can be solved as convex optimization problems. So we may be able to solve that a little bit more efficiently, at least from where I come from. When I hear the convex optimization as a term, then I say, okay, the life is nice. But the life is not nice yet. And then we can solve this geometric programming problem and obtain a feasible solution for the problem that we were dealing with. So I'm going to show you a couple of tricks or restrictions that is going to bring us to a geometric programming form. So first of all, this is one of the troublemaking terms. What's going to happen is instead of this equality, we will relax this thing to an inequality. So it's going to show itself here. And then the rest is just trivial. We will assume that this P of S, P sub S is not 0 and divided by that. That's the only part. So essentially, this relaxes the equality constraint to an inequality constraint. And because of this relaxation, we will not get the exact probability values that we are looking for, but we will get upper bounds on them. And then we end up having something in this form. So how are we going to deal with this? It turns out that all but one of these entries is a polynomial, and this extra one is a signomial. So the signomial part is the complicating part is only in one of these terms. The ugly dependence on the parameters. What we will do is, again, when I face something hard, I just close my eyes and say, I'm going to get rid of that. All right, we will introduce a new variable, and this is going to be the lifting part. So we will have additional variables now, and we will close our eyes that this is a signomial for now. So with all those restrictions, we can go back and obtain a geometric programming problem, and we can try to solve it. And since we had all these liftings and relaxations, etc., some sort of regularization, we add that to this problem statement. So the rest is, as I explained, and then we regularize it so that in this modified decision space, we try to get solutions that would probably be closer to the solutions that we would get without these relaxations for the problem that we would not be able to solve efficiently. So if you wonder, I can say that this is total hack. Don't tell to the student. But it's a total hack that seems to help. So then the point is that the solution to this gives essentially a feasible solution for the problem that we wanted, but it can be suboptimal. All right. And then the next step is, okay, now we have a way of creating feasible solutions. Can we improve it? The next step is so-called sequential convex programming. Essentially, you get a solution, around that you linearize, you get another solution, fix that as your current solution, linearize around that, do it again and again and again. Okay? No step solves a hopeless problem, at least. What happens is that it works. So for some benchmarks, Z3 offered an encoding that we could use for this initial set of results. In many cases, in many benchmarks, I think somehow it was either not applicable or something was there that we could not try it. Okay, and then this one is this hack. And what happens is that, for example, here the Z3-based solution times out, and this sequential convex programming-based technique generates some solutions. And then I guess there is no case where this method is worse than what Z3 could do on the problems that it can solve. For example, here about 2 orders of magnitude or a little bit more better computation time, and the relatively large Markov decision processes. The number of parameters are still pretty low. But then similar ideas, a different optimization solver underlying different types of relaxations could go much farther. So essentially, what I showed was that things were scaling relatively well for the number of transitions and states, but now they are also scaling relatively well for the number of parameters. That was the sticking point in the entire parametric Markov decision process synthesis problems, because they created nonlinearities from being able to handle 2-3 parameters. This way of trying to have a sequential convex optimization way of approaching this goes to thousands of parameters, and so this is working relatively Nice. And then whether these numbers mean anything, let me show you one example where actually it did something. Okay, so this is a little example where we have a satellite and some sort of discretization informed by the physics of it. This is not you take a 3D space and try to discretize it in the way that I said, but it goes and finds some orbits that satisfy the underlying physics of the problem, and then solves the discrete problem with respect to these orbits. And the discrete states are which orbit I am on and where on that orbit I am at. And then there are these other objects around it that it probably tries to not crash, etc., and tries to use least amount of fuel. And this is not even a problem with a POMDP. We also introduced uncertainties in the POMDP that the transition probabilities are not exactly known. So it is trying to solve a POMDP synthesis problem, but robustify against the transition probabilities as well, the uncertainties in the transition probabilities. And this is a pretty sizable problem. I don't remember exact number of states or and parameters, but the number of states are getting to 500,000 states perhaps, and the parameters are essentially sufficient number of parameters that it can handle so that it can come up with a policy for this POMDP. If you remember the correspondence between the parameters in a Markov chain and the controller term, the controller for the underlying POMDP. And it follows roughly the similar, just the flow. You have a problem, uncertain Markov decision process, and a specification. Straightforward formulation gives a infinitely many constraints, so-called quadratically constrained quadratic program, and a non-convex one actually. So, and then convexify it, somehow pass it to, with no loss, pass it to a finite representation of the uncertain set, solve the resulting problem. If it is satisfied, you are fine. If it is not satisfied, you inform the solution and you go on. So this way of convexifying the underlying nasty problems for finding feasible solutions for synthesis in partially observable Markov decision processes, and then improving the solutions with help from model checking, probabilistic model checking, it seems like it is I like it. So then there is no end to it. What I showed was one way of convexifying and dealing with it and making it a finite problem out of it and then improving. But then you can linearize the problem, then go to dual representation of those problems and then solve a different thing. And it also works. Actually, it works better. I just was lazy to create this slide for this version, and I just put that banner there. We can discuss them later. So this connection between convex optimization and the type of problems that we actually try to deal with in formal methods or probabilistic versions of these, I think is a very promising direction. The last bit, I'll try to make this short. The last bit is still POMDP, and I'm going to try to show you how formal methods and learning might work together, all right, for this purpose. So I am borrowing some slides from Niels Jensen for this. Niels did not know it, but thank you, Niels, if you ever watch this. So we have a POMDP and we have some specifications, some probabilistic temporal logic constraints, let's say. Synthesis is hard. So if someone gave me a strategy, I can check it. The strategy here is a observation-based strategy. It looks at finite history and tries to make a decision out of it. You take that, implement it on the POMDP, you end up having a Markov chain. Verifying whether a Markov chain satisfies something is, let's call it the easy problem, okay? We'll treat that as the easy problem here. Then the question is whether it satisfies or not. If it satisfies, we are done. If it doesn't satisfy, we are not done. What are we going to do in that case? And the next question is, who's going to give me a strategy that I can check like this? Okay, So I'm going to first address this, who's going to give me the strategy part. And so it never happened in this way around the table, but could AI give us this, right? Again, I said AI is capable of predicting when we will die. I know when I'm going to die, by the way. I used that bot and it told me. So it is a great question, but then there are also these cartoons. That's what we think that AI can do and what the AI can do. Actually, AI is going to just, sorry, I should stop using AI. Can we learn a strategy can we learn a strategy that would be a candidate for that procedure? Even if we learned, it is very unlikely that it's going to satisfy the specifications that we have in mind, okay? But can we use something like that as an initial step? So this is an ugly figure. But the point is that learn something and then improve it with help from verification. We have a PAM-DP, a specification, and initial policy. And then in this flow, we will keep track of a policy as well. So gamma hat is the policy that we have, and it is represented as something, a recurrent neural network. Okay, don't ask me what it is. It is something. Okay, it takes your finite observation sequences and it spits out a distribution over your actions, right? Just the observation-based randomized policy sense. And it has a fancy name, but why is it used? I can answer that. It is used just because it gives a representation of a policy that as data comes in, you can revise efficiently by using the so-called whatever the deep reinforcement learning algorithms do, right? So that is the only reason. It is a representation that is going to consume your data efficiently, nothing else. All right. To me, nothing else. And then we have now a candidate policy, but we cannot take that and put on a PAM-DP and model check that. We need something that is going to be has a finite state representation. So a lot of hack. Oh, by the way, every step of this thing is a total hack, but it is going to work. Okay. You go and quantize the underlying whatever is continuous, and then look at this recurrent neural network based controller does. Fix a memory structure for your finite state controller. There is a literature on that, increasing literature on that out there, but you get a finite state controller now for out of your recurrent neural network based controller. Why did this not start with this already? Go back to why we decided to use recurrent neural networks. I don't think there is a way to train a controller of this form efficiently from data. So you try to efficiently train something, extract an approximation of that. When I say approximation, it needs to be like between 17 quotes, because there is no sense of like what is the bound on the approximation error here. To try to do that. Once you have it, then you can model check it, right? If it passes, fine. Very likely it is not going to pass. So if it doesn't pass, what might have gone wrong? A couple of things. One, that your problem was not solvable. If that's the case, you can we wouldn't know that. The other sources, your recurrent neural network was not doing its job properly. Maybe you can then create some more data and try to improve that. Or your extraction of the finite state controller was not fine enough. The network was fine, but your finite state controller is not fine. You can try to add more memory, and you can try to improve your approximation of this finite state approximation of the recurrent neural network. So a bunch of hacks, again, going to this hack things, try to make a decision whether I should generate more data or whether I should try to refine my approximation of the existing recurrent neural network. And then you close the loop and you go, okay? And then this last thing shows I don't know how to erase all this stuff now here. Let me give a shot at this, if it erases things. Okay, it did. So what is that from iteration to iteration, the probability of satisfying the specification improves. This shows that. And this shows essentially that the problem-making parts of what we have is shrinking in size. Okay, and then this one shows with a fixed amount of memory. It shows as we put more data, this ad hoc metric that we use to decide whether we should increase the memory for the finite state controller, or we should try to generate more data and refine the recurrent neural network. If this thing called this average entropy of something that the algorithm generates decreases, that's a sign that you cannot do any much better by incorporating more data. You better actually now increase the memory that you use for your finite state controller. So these graphs are in the right directions, and what we have is that this is essentially gives a if it works, it gives a correct strategy, but it may actually fail even in finding a feasible strategy for your specification. So it is definitely not, your problem might be solvable, but it is not necessarily going to give you a solution. Not surprising. And then a good number of comparison on a bunch of small and increasingly large POM-DPs here. This is the state space, and then compared to Prism POM-DP. I don't know if it is always the case, but the computation time is it is better. It can scale up significantly more than Prism POM-DP. But again, it is not going to get you the optimal solution, and it is worth actually checking whether it is getting ridiculously far away results. So as for comparison, this is when it can solve on these smaller problems what Prism MDP gets, and what this procedure with the learning and formal verification incorporated gets. It is in the ballpark. It is almost never better, but 6 versus 6.02, 8 versus 8.11. Obviously, it depends on the problem that you are solving. It is in the ballpark, and it can scale up significantly more than what Prism POM-DP does. More examples. I'm gonna just show you. Just the point of it is it works. This is the last slide. Okay, I can do it in 3 minutes, maybe not. So this is where I started from. There are lots of complications for autonomy, and I tried to show you a few examples where actually just this group, including hopefully as the fly on the wall includes me, can actually go and see how we can do things with and merge ideas with different directions and solve increasingly interesting problems, hopefully. I'm not going to say more on this thing. What I'm going to try to tell you is that the sky is the limit for this way of thinking, I believe. So recently we ran this series of workshops on what is next for autonomy. And essentially, we believe that individual systems are coming along well. And so we now need to start thinking about how we can live with these things in a way that we can trust. And then this is a workshop report. And it discusses the complications or opportunities, challenges in these 7 or 9 bullet points, or the titles. And some of the common comments were, I think, worth remembering, and I think aligned with what we discussed today. So one is that, do we even have to care about assurance in autonomous systems? And no assurance, I think, in this case, is equal to no useful autonomy. We cannot think about autonomous systems with appropriate assurance on what they will do. Then autonomous systems, they inherit diverse set of vulnerabilities because they integrate functionality from different places. Hence, I think our methods needs to be aligned with that. And then in almost every subtitle, people had acknowledged, and these are not, by the way, this is not a group of formal methods people sitting down and trying to write a report that says, hey, formal methods is important. I'm not sure if we had some formal methods people, but it wasn't more than like 5 to 10% of the group of people. Everybody acknowledges that we work in an open world, and that complicates a lot of things. And then we need interdisciplinary approaches, and it should not be an afterthought. If you go and speak with all these people who are experts in these, what they will say is that, hey, this is very important, but we cannot deal with this after we build a system. This needs to come at the beginning. And I'm going to comment a little bit on what that might mean. But to me, the message there is, you cannot incorporate any of these thoughts if you don't properly formalize them at the beginning. And guess what? Formal methods has the word formal in it, and formalize has the word formal in it, right? And this is not a superficial comment I am just making here to make us happy. I truly believe in this, because in a lot of these things, there is no shortage of probably ideas. What I think the shortage is where the self-discipline, and formal methods can bring that self-discipline. Just at least you can say, even if you fail in it, you can say, let me sit down and write the damn thing that I want to do. Give me a problem statement. If you can't give me a problem statement, who cares about your solution? You know what? That obvious statement is not that common out there. We should go and teach your neighbor. And we usually discuss safety and verification. What I realized was security is extremely important. And I don't know if Moshe is here or not. We are making backward progress in security. There's a lot of problems that we can try to look into it. And then it gets broader, certification and regulation. How can we do this damn thing so that we can inform how the regulations need to be written, whether the regulations should be, how we can write the regulations so that there's a little bit of a hope actually doing these things in an automated manner, or we can scale these things up or not. There's so much interesting work out there that even the written regulations do not have any meaning, and they might even be inconsistent with each other. The tiniest, the zeroth order problem that we can try to solve should be able to actually inform that process. Privacy is, everybody is saying privacy, 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 but few people understand. Not that I understand it. I'm not criticizing the others, I'm just saying that I understand it. But here's a little example that I think gives very interesting challenges for formal methods. You have some sort of a system. It consumes data. And there's the differential privacy world out there that formalizes some sort of privacy. Not that it is the perfect, most meaningful privacy notion, but there is a mathematically based notion of privacy out there, differential privacy. It goes and introduces a bunch of new noise into your system. How can you go and verify that this new noise is not going to cause any safety vulnerabilities? Can you come up with trade-offs between the amount of privacy, hence noise, that you introduce to your system, and the safety implications of that? The list goes on pretty neatly. I suggest that you take a look if you like, and then I'm happy to discuss. But I feel like every paragraph is full of problems for us. Okay, this is a great time to be running this semester, and thank you, the organizers, whoever had come up with this idea. This is the end of my talk.
Okay, great. Thank you very much. Let's first give some virtual thank you for our speaker. And are there some questions that you would like to ask? We had a bunch of questions through the discussion, but maybe if there's some now, please either raise hand or put them in the chat. While we are waiting for people, maybe I can ask, where is this report available? Is it publicly available already, or?
I can post the link, but if you Google CCC Assured Autonomy.
Okay, that's good. So that's good that you know.
Google is much more reliable than I am.
CCC Assured. And indeed, I see it. Thank you. So maybe can I ask one question that goes back when you now kind of already start to blanking a little bit. When you were comparing your tool, Motesek, how was it the name?
Mosaic is a convex optimization solver.
Right.
Yeah.
Right. So if you look at that tool, what was? I mean, I can see that it was much faster than the C3, and well, what was the secret ingredient? I mean, I remember that you inserted that you change this equalities to inequalities, and that you argue why you can do that. And did you? Was it that because C3 was trying to solve this as a linear integer arithmetic problem, or what was such a great trade-off in the optimization in the scalability?
I will come back to you.
Okay. Sure.
I don't know.
Okay, sure. No problem. I'm looking forward to hear what was it, because that's really impressive improvement.
I cannot think of what was passed to Z3, but I will get back to you.
No, sure. Let's see. More questions?
That's
Well,
okay.
yeah, if there's no questions, then Rainer, sorry, Rainer raised hand, please, Rainer.
Yeah, I have a somewhat speculative question related to that. So kind of the final success stories that you showed us, it was kind of something which you called hack, which is essentially, I mean, I wouldn't call it hack, I guess it's engineering. And then on top of that, you have in order to get the guarantees, on top of that, you apply a formal methods tool, and then you get some kind of safety guarantees and maybe sacrificing performance. But so do you think that that's the kind of that should be the way that we should kind of be thinking forward, right? How to is there more scope for bringing kind of the two worlds closer together in terms of trying to develop methods that are kind of not hacks from the beginning, but kind of more principled in terms of development?
I am in no position to say what we should be doing. What I can say is that this is one thing that one group of people has done and tried and got results. It would be, obviously it would be better if you can bring people together and try to develop dedicated tools that are less engineering, more principled. I don't disagree with that at all. And I think
I mean, yeah, the question was whether one can do better than that. I mean, maybe it's not really possible, really, or easily solvable to kind of.
Yeah, one thing that is a little bit clear, just so that we have a discussion, whether there is going to be a principled thing, a less hack in some way, or less engineering. Let's remember that there's a reason for us we had gone this route. We know that there is not going to be a efficient solution to these problems, right? So in my mind, this way of thinking should never be the first thing that you do. If you face a new problem, at least understand the complexity of the problem first. Maybe the specific problem that you are trying to solve is not as hard as what is known out there. Try to come up with a precise complexity description. If you are convinced that now a principled way is hopeless, which is just you prove it, not just you have a hunch for it, then I think it is fair game. Try these things. I have a similar discussion with my students often on whether we should just abandon what we are doing and train neural networks. All right. And as a conscious advisor, I cannot tell them not to use neural networks. But what I tell them is, I tell them what I just told you. Go and prove me that the specific problem that you are trying to solve, is hard, hopelessly hard. Then you do whatever hack you want to do. So I think this should be hand to hand. And again, just putting discipline on you, and this process might even tell you how to modify your problem so that you might come up with a subset of the problem that you did not need the more general thing that you can have a more efficient solver, etc. Yeah, I am in no position to tell people what to do. Don't give up on any of the possibilities. Limit your use of things that you don't understand.
Thanks.
Yep.
Okay, so I guess you promised that we will be done way before the time, and look at us, you gave such a good talk that we ran way over, well, a little bit over time. So thank you very much, Ufuk, and let's stop here. And I mean, we still have whole semester that we will be able to discuss these interesting topics. Oh, Noemi, do you have a quick question, or is it long? If it's long, then you will have to ask offline. Noemi? Or that's, is it? No, that's not raised hand. Sorry. Okay, then let's stop here. And thank you very much. And have a good weekend. And see you soon. Bye, everyone. Bye-bye.